Welcome to this live session. The idea of this live session, before we start the actual course, is that to get clarified some overall doubts which you may have about the course. Let's say about the scope of the course and which year students can take the course and whether this course will be suitable to you or not. And you would have looked at the brief introduction and the detailed introduction video, and you may have some questions based on that video as well. So this live session is to answer such kind of, I would say, very superficial questions, may not be very specific to the subject, and so that it will help you to decide going ahead with the course and what you can expect from this course and so on. Let me start with the questions which have got in the response sheet. I'd like to take up a very good question asked. Why we are studying continuum mechanics? It is a physics part. That's a very relevant question because the title of the course itself is unique, I would say. Continuum Mechanics and Transport Phenomena. I'd like to also tell about the genesis of this course. We did a curriculum revision about 4 years back, and then we were supposed to reduce the overall number of credits, which means reduction in the number of courses and core courses as well. So we were trying to consolidate the core courses, and when we are trying to consolidate the transfer phenomena based course, we thought we'll have an introductory course on transfer phenomena so that other courses on transfer phenomena, namely fluid mechanics, mass transfer, heat transfer, can take on from this where this course leaves you. And that's the overall scope of this course, and that's why it is pitched at the third semester, fourth semester level. And one more objective was to make it as a science-based course, closely associating this with physics, and that's why I'm answering this question first. And that's why the course has two components, namely continuum mechanics and transfer phenomena. Students at the third semester would have done a course on rigid body mechanics, and now we are going to extend that to deformable solid mechanics, wherein we are going to study analogously fluid mechanics also. So that brings a very close association with physics, what you have studied. Not alone that, not alone fluid mechanics, even for energy balance and then species balance, even of course total mass balance, we always are going to start from the law of physics, and from there on we're going to derive the conservation equations. So you will have a very you will realize the close association between physics and the conservation equations used in chemical engineering. Usually the transfer phenomena course is in the 7th, 6th semester, where this link may not be so clearly visible. It is still there, but based on the course being taught at the 6th or 7th semester, and that link may not be so clearly evident or visible. And keeping all this in mind, we propose this course for the third semester students. It is being taught at IIT Madras for the third semester students, just after their second semester introductory physics and or basic sciences courses. And so it also brings forth the science part of chemical engineering. In fact, we have a journal called Chemical Engineering Science. So, and of course, the second paradigm of chemical engineering brings forth the science part of chemical engineering, and this course is in line with that. Okay? I would like to acknowledge Professor Abhijit Deshpande in our department, who came up with this idea of proposing this course on continuum mechanics and transfer phenomena, and which was brought into the new curriculum. And I've been taking this course for the last 3 years, and I thought I'll share that with other students across the country as well. And that's the genesis for this course. Okay. Let me answer another simple question. I would say, what are the books to be followed? The question is, which book would you prefer for undergraduate students for the coursework? If you look at the detailed introduction which has been uploaded, towards the end of that, I discussed the books. Several books have been referred based on this special scope of the course. Not one book all these needs or the scope of this course. So we require books on fluid mechanics and solid mechanics, because we're going to look at the analogy between these two, study very closely solid and fluid mechanics. And we also, of course, require books on transfer phenomena. So if you look at the end of introduction, you will find out a few books listed there. For example, fluid mechanics book by Fox and McDonald is, I think that is used throughout the course very much. And Sengel is a very good book in terms of colorful representation, simple explanation, etc. So those two books of fluid mechanics. And for solid mechanics, we use a book by W.D. Means, an old book, and by Raymond Barnes, that precisely suits the scope of the course as well. And of course, for transfer phenomena, of course, no other book comes before Bird Stewart Lightfoot, and that's a book we are following, the first edition of that. And then another book by Will T. Wicks and others. That's again a very excellent book, Fundamentals of Heat, Momentum, Heat and Mass Transfer. That can also be referred for the transfer phenomena part. Also like to mention, the continuum mechanics is a very mathematical subject. If you look at a typical book on continuum mechanics, if you go to web and then or a bookstore and then look for books on continuum mechanics, they're highly mathematical. And this being featured the third semester students, throughout the course, we hardly require any sophisticated mathematics. A lot of physics is required. That physics is put in simple mathematics. So most of the time we arrive at the same physical conclusion in a more physically intuitive way, in a sometimes let's say geometrical way, analytical way, rather than more mathematical way. And that has been kept throughout the course. So if you are looking for a very formal continuum mechanics course, this may not be suitable, but all the principles are covered here in a very simple way. And whatever principles required to study fluid mechanics and solid mechanics, that are brought throughout. Okay? So I would say introductory continuum mechanics course is the scope of this course. And with this knowledge, you'll be able to follow a more advanced continuum mechanics course. Especially, I see a lot of enrollment from mechanical engineering. So this could be considered as an introductory continuum mechanics course. And then this will be a stepping for physical introduction to a more mathematical continuum mechanics course, which you may take in your part of the curriculum. Okay. And okay. There's a question here. Can this course be used by a mechanical engineer who is pursuing research in energy storage? And there is an allied question. Let me read out that question as well. I'm a computer science graduate and aim to do my further work in the field of plasma simulations and modeling. To improve my understanding of the subject, I've enrolled in this course. Is this course right for me? And what topics do you recommend? that I should do simultaneously or in future, which might help in the field of plasma magnetohydrodynamics. This the topics covered in this course, continuum mechanics and transport phenomena, are very general. Okay? Something I can say, we are going to derive the all-encompassing governing equations, and which has application in several fields of engineering. And so we'll have fundamental introduction to the governing of all the derivation of all the conservation equations, including all the physics. But now, when you are looking at some special applications like plasma, or let's say, of course, as he says, energy storage, lithium-ion battery, some more physical phenomenon may have to be taken into account, or will have to be taken into account. Okay? That requires reading books specific to those fields, but they would once again start with all these conservation equations, especially if you're looking at simulation, and you will have some extra terms there. Okay? And if you follow this course, it will be very easy to extend your knowledge to other special areas, like, as he says, plasma or energy storage, etc. We are not keeping any special field in mind and discussing this course. It was introductory third semester, fourth semester course. So it's kept very generic. And for research purpose, this course will certainly give a very clear introduction and introduce in such a way that you can extend to other special fields as well. Okay? So that's the scope of this course. And there's one more course, one more question here. That's on a little more specific. I wouldn't say not within the scope of a live session, which we have before the start of the course, but still I like to answer that. It says, in mass momentum energy balance equations, if process is isothermal, then does the energy balance equation drop out? Now the answer to this question depends on whether we are looking at the integral balance or the differential balance. Of course, as I told you, this question is a little more into the subject, but Avanti Kumar Patel has asked this question, so of course answering is him. If you are doing an integral energy balance, and if you are maintaining a process under isothermal condition, some energy has to be supplied. So in the integral energy balance equation, temperature becomes known, and you can solve that equation to find out the energy to be supplied or removed. So you'll still have the energy balance, but you will solve for energy input. But if you are not concerned about energy input, then that equation need not be solved. Now coming to the differential balance, because it is isothermal, you need not solve the differential energy balance, because differential energy balance is solved for finding the temperature profile. If it is isothermal, it is uniform throughout, and hence you need not solve the differential energy balance equation. That answers. Okay, I have one more question from Deepak Sharma. Is this course has any significance for computer science? May not be directly for computer science. Tomorrow, as given in the course website, this course is equally applicable equally relevant for mechanical engineering students and chemical engineering students. Though, of course, I am from the chemical engineering department. The mechanics part, the chemical engineering students will benefit from the mechanics part, which may not get stressed in the usual courses. And for the mechanical engineering students, of course, they do mechanics, energy balance, etc. They will benefit from the mass transport part. In my course, I offer this course at the postgraduate level also, or advanced level. I've had students from mechanical engineering, of course, chemical engineering as well. I've seen mechanical engineering students benefit from the diffusion phenomenon, mass transport phenomena, which will come, of course, towards the very end of the course. That way, it will benefit both of them. And next allied branch is biotechnology. Biotechnology and chemical engineering have a lot of courses in common. But usually biotechnology students do courses together. For example, they may study mechanical and fluid and particle mechanics together, and then they may have one course on heat and mass transfer together, and they may also have a course on transfer phenomena. So in that way, this course will be, because they also deal with fluid flow as well, and reactions, mass transport. May not be not much with energy balance. So this course will be useful for biotechnology students as well. Okay. Of course, other branches of engineering which involve fluid flow, for example, aerospace, ocean engineering, and civil engineers will also benefit from the fluid mechanics part, and of course, energy balance part as well. So computer science, I wouldn't say is an allied course, allied branch to this course. Okay. I have another question from Brajesh Kumar Kanchan. Do we need any sort of software for this course? No. The first question is no. But throughout the course, I have shown several simulations so that you get a very good physical picture of the physical phenomena. For that, I used MATLAB. So if you are interested to reproduce those simulations, then you can, out of your own interest, you can code them in MATLAB, and you also can reproduce the simulations. But as part of the, let's say, so-called curriculum, so for evaluation, for the main part of the course, you don't require MATLAB. Of course, there are certain graphs plotted in Excel, so you can reinforce your learning yourself by using Excel, MATLAB, but as such, MATLAB, Excel are not required, because all the calculations are going to be, maths is going to be very, very simple in this course. And we'll have simple algebraic rearrangements, simple calculations, simple differential equations. Only if you have a little more complex equations, complex nonlinear equations, and then partial differential equations or simultaneous ODEs, then you require nonlinear ODEs, then you require software. But within the scope of this course, maths is very, very simple, but of course very physics rich, no doubt about it. We express all that physics in terms of expressions, equations, mathematics, and of course supported with a lot of engineering applications. As far as possible, throughout the course we discuss engineering applications. We try to avoid simple mathematical applications, meaning given expression, find out this, etc. We try to avoid as much as possible. Always linked to an engineering application, be it chemical industry or even day-to-day examples, etc. Okay. That's what is kept in mind. Okay, I have another question about the assignments that is to be assigned. Will they be based on the books referred in the course introduction? I would say to some extent, yes. We are trying to base the assignments on the books referred in the course introduction. I wouldn't say completely or confining to them, but assignments will be certainly within the scope of coverage in the lectures. We hardly would go out of the scope of the topics covered in the lectures. So if you listen to the lectures and then of course do the relevant reading. See, we have referred several books doesn't mean the entire book has to be, all the books have to be read in entirety. You will have to read major parts of the book. For example, we have referred a book by Raymond Parnas on solid mechanics. That's a full book on solid mechanics, but we are going to use only, let's say, the first few chapters, 2-3 chapters or 4th chapter, that's all. So you'll have to refer those chapters in that particular book. And I was talking about WD means a very good book. Once again, of course, you can read the entire book as well. A very, very nicely written book. You'll become an expert, I would say, in solid mechanics. And so that book can be read in entirety. And once again, books on fluid mechanics by Sengel and then Fox and McDonald have a wider, larger scope. A lot more is covered in that book. So please, when you read those books, restrict to the topics which we are discussing. Of course, you can't afford to read the entire book as part of this course. You may have to cover it in some other course, but as part of this course, we take parts of that book which is relevant to us. We keep the scope of this course very much in mind. And similarly, the transfer phenomena books, Bird, Stewart, Lightfoot, Wilty, Weeks, etc., many more topics than we are going to cover in this introductory course. So once again, we can restrict to the topics which are relevant to this particular course, and also to the level, to the scope which we are constraining ourselves to this course. Once again, want to repeat, it's an introductory course, so that you can follow it up, or rather I would say you should follow it up with another course on fluid mechanics, another course on heat transfer, and of course mass transfer. You would require 2 more courses to complete your knowledge on momentum, heat and mass transport. And that's how we defined this curriculum here in IIT Madras, and eventually we saved 1 core course, because we are to reduce the number of core courses, and that's what we have achieved. So let me go to the next question by Krishna Kumar. Is this useful for aerospace engineer to understand fluids and tensors? Yeah, a relevant question, very relevant question. Well, whichever course has fluid, whichever engineering discipline has fluid flow, this course will be relevant, no doubt about it. Okay? So aerospace engineers will benefit, but we usually look at incompressible flows, flows at lower Reynolds number, lower velocity flows. Aerospace engineers, of course, you look at very high velocity flows, you look at compressible flows. Those will not be covered here. Okay? That is not the scope of this course as well. So in that way, and that part you may be missing. We hardly discuss our compressible flows at all throughout the course. We restrict ourselves only to incompressible flows. Okay? So in that way, you may lose out something. But as general introduction to fluids and mechanics, this course will be certainly useful to you. And asked a question about tensors. Tensors is a advanced mathematical concept, and is advanced for a typical, I would say, BTech curriculum. But what we have done in this course is they are physically very rich quantity. Just to tell in one line about tensors, those who are listening are not aware of tensors, we have scalars which are used to represent physical quantities with only magnitude, for example, density, temperature. Vectors are used to represent physical quantities with one magnitude and one direction, like velocity. And there are physical quantities which you'll come across in this course, which require a magnitude in 2 directions, and those are represented by tensors. In this course, we do introduce tensors very gradually. I would say introduction to tensors, very minimal introduction to tensors. We won't look at tensor operations, vector tensor, tensor calculus, and so on. But you do get a physical introduction to tensors. In fact, I have one small lecture as part of a big lecture on introduction to tensors. So at the end of the course, you will have some introductory knowledge about tensors. You would have got some physical significance of tensors, and that is kept throughout. In fact, many a times I won't even distinguish tensors and matrix. I would say matrix are tensors, tensors are matrix. So that's a level of tensors we discuss in this particular course, not rigorous tensor calculus, tensor algebra, etc. That is for an advanced course. Is this course useful for microfluidics? Of course, no doubt, certainly useful. Certainly useful. Okay, it's microfluidics is a branch which deals mainly with fluid flow through, let's say, geometry of small dimensions, and it's predominantly deals with fluid flow. And this course is all about fluid flow, so certainly it will be useful. For if you're working in microfluidics, if you are trying to simulate some flow in microfluidics, and if you're doing experiments in microfluidics, certainly this course will be useful. Okay? Yeah, yeah, nice to hear from Rajesh Kumar. Just thanks me. Um, Looking forward to stay with the course. Yeah, I also look forward to you in the course as well. Okay? Let's interact in further sessions as well. Yeah, that's good, Rajesh Kumar. Okay, those are the questions as I know I have as of now. Let me see if I have got anything in the online response. Yeah, there is a question, not of on the technical front. If we miss out the live session due to some non-avoidances, would you give us the chance to access the video again? As I understand, I think this video is recorded live and will be available. I think almost right from this moment on YouTube, and the link has been sent to you. And so I think anytime you can access the link. So even if you're offline, later on you can come and watch this live session. It's being recorded, and so it's available to you anytime. Answer the questions received so far. For more questions. Okay, maybe in the meantime, I can tell something about the course who are online. We, you would of course follow the introduction. You would have seen the course overview slide there, okay? And I would say, strictly follow that course overview slide, starting with fundamentals, and those fundamentals are covered usually in a fluid mechanics book. But the way in which we discuss, it is emphasized that those fundamentals are common to the entire course. Though it is covered in fluid mechanics book, those concepts are required to understand fluid mechanics and energy balance and species mass balance as well, and of course total mass balance as well. Then of course we a lot of emphasis is put on deriving the conservation equations from the law of physics as explained in the introductory videos. The moment we say derivation, some feel it is boring and so on. But you'll see as you go along, derivation will be a very enriching experience. That more so when we really understand the significance of each term. When you do a derivation and write, let's say, equation governing, let's say, mass balance, and then a thorough derivation would tell you what is the significance of each term there, what are the assumptions behind it, under what condition you can apply, not apply, and so on. Okay, and so then of course we derive the linear momentum balance, and that's where we parallelly study fluid and solid mechanics. We in fact go back and forth between these two and look at the close analogy between solid and fluid mechanics for two reasons. One, in keeping in mind the scope of the course continuum mechanics. Other, many concepts are easily understood through solids. That is one reason we, I would say, learn fluid mechanics through solid mechanics. Of course, look at the analogy as well. And you'll be really happy to see that many concepts are analogous. And of course, we derive the conservation equation for linear momentum, which we use for solving velocity profiles. And then I want to emphasize one particular part of this course, one I will say peculiar aspect of this course. Fluid flow is our fluid flow can be analyzed from mechanics point of view. That's why we study solid and fluid mechanics. But fluid flow can also be analyzed from a momentum transport point of view, because you'll know details as you go along. So if you look at a transfer phenomena book, fluid flow is analyzed from a momentum, transport of momentum point of view, molecular transport of momentum, etc. And similarly, energy transport and species mass transport. This course combines continuum mechanics and transfer phenomena. So the fluid flow part will be analyzed from a mechanics point of view only throughout the course, okay? Except one lecture where we connect both the viewpoints, where we discuss fluid flow both from mechanics viewpoint and transfer phenomena viewpoint. Okay, so we don't discuss momentum transport at length, but discuss so clearly the analogy between them, because the end result is going to be same. Let's say you're solving a velocity profile, either you take the mechanics viewpoint or the transfer phenomena viewpoint, is going to be same. We emphasize on the mechanics viewpoint, which you typically come across in a fluid mechanics course. But very importantly, in that particular lecture, we also look at what's the similarity between the mechanics approach and the momentum transport approach, so that you'll be able to analyze problems in both viewpoints, either mechanics viewpoint or a momentum transport viewpoint. Okay, so we just spent only a lecture or a half or lecture or two on momentum transport. By the time you would have understood very clearly about the mechanics viewpoint of solving fluid flow problems. Of course, and that is also required because transfer phenomena is also a part of the course. So that will help us to have an analogy between momentum transport, heat transport or energy transport, and then species mass transport. So keeping that in mind also, we discussed the momentum transport viewpoint of fluid flow. And I would say that is something very unique to this course and special to this course, because if you have fluid mechanics course, they would view fluid flow from mechanics viewpoint alone. If you are taking a transfer phenomena course, and that would view the fluid flow from a momentum transport point of view alone. But we discuss both of them. We go from, I would say, solid mechanics to species mass transport. So keeping the scope of this course in mind, we have a class where we discuss the analogy between what way they are similar, what is the subtle, small subtle difference between the two approaches, and so on. Okay? And that I like to, of course, emphasize in this live session as well. Okay, so those are the questions I have on the response sheet and in the live session as well. Okay, of course, we have left with about another half an hour. Students. Okay, so just to continue with the, I was talking about the course overview, and we follow the course overview, and I was talking about the derivation of conservation equation of momentum for fluid mechanics, and then of course we move on to energy balance, derive the conservation equations for energy balance, so that we can solve for the temperature profile, and then later on also we derive the conservation equation for species mass. And what we do throughout the course is we keep in mind that the same steps, I would even call recipe, is followed in deriving all the conservation equations. That is once again kept in mind throughout the course. We arrive at that, let's say, recipe or procedure at the end of total mass balance, and following the same steps, we derive all the other conservation equations. That is also a objective of this course, that the methodology with which we derive the equations are same, be it whatever conservation, whether it is total mass balance or conservation of momentum, energy balance, or species mass. Okay? And so that is kept in mind throughout the course. And also we look at the analogy between the equations as we derive. For example, once we derive linear momentum balance, we compare that with mass balance. What are the extra terms there? When we go to energy balance, once again we compare all three and see how are they comparing, how are they differing. And then of course at the end we compare all the four equations and then see our three equations and then compare and contrast and so on. Okay, and so that analogy is also kept in mind throughout the course. And coming to applications, throughout the course, we look at a lot of engineering applications, numerical applications, and that will help to emphasize the theory we have discussed. As far as possible, after discussing every concept, there are applications that has been kept in mind to reinforce the theory. Of course, given the limited hours of recording and time for this course, we can't solve many applications, but representative applications are solved throughout. For example, even for differential mass balance, integral momentum balance, we do solve applications which have different types, so that following those applications you can solve the assignments. Of course, that will help you understand as well. And also like to tell some of the students may have question, especially students in the higher semesters. Let's say you have the 6th semester, you may have a transfer phenomena course, or you may be taking transfer phenomena course. For them, of course, this is also highlighted in the detailed introduction which has been uploaded. You can take a look at that slide as well. What are the differences? One difference, as I have told you some time back, a typical transfer phenomena course in the higher semester would view fluid flow from a momentum transport point of view. Here we are viewing fluid flow from a mechanics point of view. Other than that, energy transport and mass transport, species mass transport are exactly same. Okay? And this, of course, at introductory level, this course. So in terms of application, there will be much simpler applications. You will solve more involved application in your transfer phenomena course at the higher semester. That has to be kept in mind. Keeping the simplicity in mind, I think this also is relevant for the live session today. Throughout the course, almost till the end, we work only with Cartesian coordinates. Okay? So cylindrical coordinates are more practical. You always have fluid flowing in a pipe, not in a cuboidal section or a square section. But that is only a geometrical complexity. So to avoid that, to focus on physical concepts, we keep the geometric complexity very simple. And that's why we always throughout the course discuss only Cartesian coordinates. But at the same time, towards the very end, we discuss cylindrical and spherical coordinates so that it makes the course complete. And I use that opportunity also to discuss what is called shell balance. I think this is also relevant to viewers, learners, students who are in the higher semesters. Once again, in transfer phenomena course, more emphasis is put on shell balance technique, which are balances specific for a particular problem at hand. But what we do throughout the course is solve problems from the conservation equation point of view, and but also to cover shell balance and also to cover cylindrical spherical geometry. Towards the very end of the course, we solve problems in cylindrical and spherical coordinates through shell balance, so that it covers both the, I would say, left out topics. Shell balance would not have been covered throughout the course, and we would not have discussed spherical cylindrical coordinates. So both are put together and I would say briefly covered, but that would be sufficient enough for you to do more sophisticated examples. So that's how the course has been planned, and I like to emphasize that as well in terms of. So you will see only purposefully I would avoid any example on cylindrical spherical coordinates till the very end of the course, and we would take up examples on cylindrical spherical coordinates at the very end of the course only. That's once again I would say as something difference between a typical transfer phenomena course and this present course as well. And of course, one other difference would be will always be linking to the laws of physics. Yeah, that I think answered the first question, which may not very much come out in a higher semester transfer phenomena course. It is certainly there, no doubt about it. But here we emphasize that. Here we really emphasize that. Every time we start the law of physics, and for example, we start with Newton's second law of motion. From there, we arrive at the linear momentum balance. From there, we arrive at Navier-Stokes equation. So, and then we start with the first law of thermodynamics. From where we arrive at the energy balance. So that has been kept in mind throughout. And the course contents have been designed based on feedback from students. The first time when I offered this course, the structure was different, and based on I would say enough feedback from students, I strongly depend on feedback. So I like to in fact welcome a lot of feedback from you learners as well. Whatever you feel, this first time being offered online, so there is certainly scope to improve upon it next time when I offer. So please feel free to offer feedback. So this based on feedback, I could rearrange the structure of the course, and henceforth it has been the course has been well connected and well received by the students as well, and that is a structure we are following here. Rajesh Kumar Kanchan has one more question, not I would say technical, but I'm new to SWAYAM portal. Can you put some light on it? I think the administration, I'll put forth a question to the team, and they will be in a better position to answer this question on SWAYAM portal. Okay. The scope of this live presentation is on the course. So, of course, I think many learners should be new to the SWAYAM portal. I can suggest one more thing option to you, Brajesh. You can send an email to my TA. He can also help you in going over this SWAYAM portal as well. Because the administration, NPTEL administration can also help you. And my TA, in fact, that's easier also. That's one point contact. Just send an email in the forum, and in fact, it will help others as well. And if we can put your question a little more specifically, for example, you are not able to navigate a particular part, or you like help in navigating, or NPTEL may have some video recorded which will help you to navigate. So those are the ways in which you can become comfortable with the portal. And that's the reason we have something called 0th week. That's why we uploaded some videos in the 0th week itself. Though the first week starts from 29th, keeping many learners like you who would be first-time learners. That's why we had a 0th week where we uploaded some videos and had a 0th assignment as well, so that you become comfortable with that. Okay? So of course you can write to us, the TA, and he will help you. If you can give more details, what exactly you want, that would be better. Okay, so well, left with some 15 minutes. Okay. So let's wait if we are getting a few more questions. If you are online, let's see if they have some questions. Some few students are online. We'll wait for a few more questions. You can ask questions on the scope of the course or some general topics, some vague idea. That is a idea of this live session as well. It could be a very simple question as well. Doesn't matter. Of course, you can ask questions in the forum as well. My TA will answer those questions. Of course, if he finds it difficult, I'll also answer those questions. And in terms of prerequisites, because those are mentioned, not too many prerequisites are there for this course. Okay, in engineering mathematics at the level of simple calculus, okay, that's all is required. Very simple calculus. Some vector calculus may be beneficial. I wouldn't say required, because certain equations can be nicely represented in vectorial form. Okay? So that's not really essential, but throughout the course I represent in the expanded form and the vectorial form also. So if you know, for example, let's say what is a gradient, what is divergence, it will help you to appreciate certain parts of the course better, and that's all is required. And simple numerical calculations are required. No special sophisticated mathematics is required. Of course, your physics should be good. And in terms of thermodynamics, I put that as a requirement at the level of the laws of thermodynamics, not beyond that. Okay? Because we are going to start from the first law of thermodynamics. So you should know about what is first law of thermodynamics, what are the different laws of thermodynamics. So that's all is required. And then I also said as one requirement as introductory chemical engineering course. Okay? Of course, mechanical engineering students would not have had that, but that would not be a major deterrent, because that is only required to know how certain equipments operate. For example, I would say absorber. So that you would have come across in a introductory chemical engineering course. But beyond that, nothing much is required. Heat exchange, of course, mechanical engineering students should know very well. And maybe reactors. Apart from that, only to know the operations, introductory courses required, and that is only when that is required only in the one or two lectures. Otherwise, the prerequisite required is just your first year courses in engineering, a physics course, a thermodynamics course, a mathematics course. So only those. And as I told you, we want to bring in the science aspect of chemical engineering, and so keeping that scope in mind, that's all is required. Okay? That is why it is pitched at the third semester as well. And yeah, that's all is required. Any? So we have a few more minutes to go. So if you have any questions, like to answer then. In terms of coverage, also like to mention this. Towards the beginning, it will be little more heavy compared to the later part of the course. So please keep that in mind, because fluid mechanics is more to do with vectors, and of course, moment you have vectors, it is in general velocity is a vector, and all others are scalars. So obviously, we'll spend more time on fluid mechanics. That's typical of any transfer phenomena course as well. That deserves so much time as well. We also have this that will reflect in this coverage also. We'll spend more time on fluid and solid mechanics, and relatively less on energy balance and species balance. Also should keep in mind that the fundamental concepts, whatever, let's say, whatever lecture hours devoted for fundamental concepts, should be spread for fluid flow, energy flow, and species flow. It is, though we tend to club that with fluid mechanics, and that is certainly brought out in the lectures as well. For example, even begin with, I will take examples on temperature, concentration, certainly to emphasize that those are all fundamental concepts which will help you to understand fluid flow, energy flow, and species mass flow. And as I told you some time back, a lot of simulations are there throughout. As far as possible, I try to fluid mechanics has some abstract concepts as well. For example, you would come across fluid mechanics, it says system, particle, etc. So as far as possible, I try to show them as in terms of simulation, something like a virtual, I would say virtual particle, virtual system, etc. So that you get a physical feel of those concepts. So do follow those simulations. You will enjoy those simulations as well, and those have been done using MATLAB. It's you want to simulate them, reproduce them. Of course, you can do that. It's simple, but to begin with, you can look at them, and then some of them are colorful. You can enjoy them as well. And that's a feedback I received while recording these lectures as well. Okay. The videos were helpful to understand the concepts as well. In terms of mode of lectures, you would have seen in the introduction videos as well. All of them are through PowerPoint, okay? And I will have, of course, I use the marker to show certain highlights, certain text, and so on. That is there, of course, throughout the lectures. But otherwise, it's all has been put in, I would say, very formal PowerPoints. And moment PowerPoint, there is some lack of connectivity. To compensate for that, I've animated all the equations and text almost throughout the courses, throughout the lectures, so that you know how equations are written. And that's advantage, of course, when you write. But since I have put them as PowerPoint to kind of, I would say, compensate for that, I've made all the equations animate. So you can see how equations are being written. And so as you write, you'll also know the significance of each term and what comes first, next, etc. What is the role of each inner term? What is the role of each variable, etc. On that, keeping that in mind, the equations are animated throughout. So of course, that makes it a little interesting as well. Okay. So of course we are almost towards the end of the live session. So of course glad to see all of you live, and looking forward to interact with you in future as well. I hope you enjoy this contents of this course. So once again, I want to emphasize that I depend strongly on feedback, and I believe on continual feedback, meaning like something like a continuous assessment. Okay, like you are assessed continuously. I also like to receive feedback now and then. Of course, you have a weekly feedback option as well, so that whatever possible, because many recordings have been done, whatever possible we'll try to rectify. That I do in the regular class as well. Okay? I do ask feedback during the semester as well. Okay? Similarly here as well. So do give your feedback. Whatever possible we'll do, because the recordings have been recorded, the videos have been recorded. Some may not be possible, but that we can maybe compensate in the live session and so on. Okay? Yeah. Now I got a question from Sarumati. Sir, as a student pursuing chemical engineering, I would like to know that will this coursework support GATE exam? And certainly yes. The GATE exam, the question papers are set in such a way that it checks your understanding. Okay, the GATE question papers are kept in set in such a way that you don't require almost a calculator. Okay, you should be very thorough in the concepts. Then you can just work out in hand and then answer the question. Okay, that is kept in mind while setting the GATE question papers. And so now this particular course, I would say, is a physics rich, fundamental rich course, no doubt about it. You will learn a lot of concepts throughout the course. Okay, and certainly that's going to help your understanding of the fundamentals. And that is, of course, it is pitched at the third semester level as well. We spend enough time on the fundamentals. Okay? That's why our applications are all not so sophisticated. Okay? You are made thorough the fundamentals and left at introduced to applications, I would say. Okay? And so any course which helps you to improve the understanding will help you in taking up the GATE exam, better facing the GATE exam. Okay? I have not answered the question directly, I would say, because whether can I say questions from this course will come in GATE exam, I have not answered that question. But in general, this is a fundamental course. Okay? So your fundamentals will certainly be improved by taking this course. So certainly it would reflect in your GATE performance as well. Of course, you do have questions in GATE from fluid mechanics, certainly. You do have questions from heat transfer and mass transfer, but certainly all those questions cannot be answered by taking this course alone. This only puts you, introduces you to all these subjects of fluid flow, energy, and mass flow. Okay, so you should take this course, and as I told you, one more course on fluid mechanics, one more on heat transfer, and two more on mass transfer. Then you'll be able to answer related questions in GATE exam. So this forms a pillar for all those courses. Yeah, I have a question on upcoming. Is there any upcoming workshop for new SPOC? Of course, not so related question, but still, I think our administrator they have answered that. It'll be informed on the NPTEL website. Okay, so please be on the lookout for any announcement on the upcoming workshop. Okay, I think we had a good live session of 1 hour. Okay. So best wishes to all of you, and hope you have a very enjoyable learning in this course. and looking forward to be in touch with you as well. See you then. Bye.